Okay, I offered a bonus for you all last class. If anyone did that, I'll take that now. Okay. Any issues with them? Do you feel confident you got it? Yeah, think so? All right, we may go over them, I'm not sure. So we're going to start the next section today, but we had already started the section. We took a little detour to talk about how you come up with parametric representations of surfaces. I don't know, I was sitting in my office before class, and I just felt like maybe we would spend maybe 10 minutes just talking about, it's kind of like an overview of the integrals that we've looked at like since Cal 1 through here, because there's a lot of integrals now. So I thought what I would do, and I'm totally like unprepared for this, it's just kind of just out of my head type thing. Want to look at integrals, and I want us to focus on the domains of the integrals to start with. So let's say that I give you the domain of some function, and I tell you that it's just a straight line. So let's say, I don't know, all the values x between a and b. I know that looks weird, but that's our domain. You're allowed to pick points on that number line between a and b. Then what we did from that is we said, well, imagine that there's those numbers, those values in here are going to get plugged into some function, right? And then what we want to do is add up all those values. Well, that would be the integral from Cal 2. That would be it right there, right? That's what it would be. And this dx, the idea here was the dx represented this little infinitesimal change in x, right? Yes, yes, yes? Okay. So this is a one-dimensional domain, isn't it? The domain is one-dimensional. But we can have integrals where our domain's in 2 dimensions, right? So we could have something like, I don't know, maybe we have some sort of path, some sort of curve, right? So this, we called it like C. And what we could do is, just like we defined here, all the values x between a and b, we have to somehow define this curve. And we did it 2 different ways. One way was we came up with parametric equations. So we said x is some function of t, and the y is some function of t, and t is between 2 constants a and b, and that would draw our curve, right? And we said, okay, well, we could also do this kind of in a vector form. We could say, use the vector function, r of t is x of t, y of t. And that was just another way of writing this, right? This is the vector form, this is the parametric form, that's your vector form. But then we could start doing integrals with this, right? So what are some of the integrals that we could do here if this is our domain? What sorts of integrals do we have for that? Line integral, right? Our line integral, right? C, we're integrating over the curve C. And then in here, we could have some, I don't know, some scalar function, right? We could have some function of x and y, and then we'd be integrating this with respect to what? S, little s, which was with respect to arc length, right? But we could also do it with respect to x or with respect to y, right? So there's like 2 other ones that go with this. What if we just, so what would this give you? Like, we know that this right here would give you like the area under this curve, right? And we could visualize it because this one would be your domain you can visualize on the ground, right? A, B. And then that function of x you could put in the second dimension. There's your function of x. And then what you're doing is you're just adding up all these heights. And so that corresponds to the area under that curve, right? That's what this is. But what is this line integral? Like, what's a way we could put some meaning on it? And we did this. We put a meaning on this integral. What was it?
Was it like curtain?
Yeah, it was like the area of that curtain, right? It was the area of the curtain. So you draw this. This is what goes in. So the domain is on the ground. Goes into this function of two variables. So that's your surface. You drop the curtain down, right? That works great in two-dimensional, when you have 3D, 3 dimensions, right? Another way to visualize this without that surface idea in the curtain is to think that if this were, let's say, like the density function, then what this is doing is it's adding up all the masses along the point, along the curve, and so this would give you like the total mass of this wire, curved little wire. Does that make sense? So there's multiple ways to visualize this. What if we did just this? What would that give you? It's kind of like what we did before when we had like 1 dA was the something or 1 dV was the something. What is 1 ds going to give you?
Length.
Just the length of this curve. That's all it is. This is just basically that's your arc length right there. So you're just adding up all the little infinitesimal arc lengths. So this right here was all these little infinitesimal arc lengths as you move from point to point along this curve, just like the dx was adding up all these little infinitesimal little segments as you move along this straight line, right? Kind of make sense? Okay, and what else did we do with integrals in two-dimensional space? We're kind of out of order here a little bit because we're starting here. That was Cal 2, and then this one is like chapter 13, right? But we did a lot of stuff between chapter 10 and 13. Double integrals, right? So we did double integrals. What we looked at was, okay, our domain was two-dimensional, and the first thing we started with was a rectangle like that, right? So I'm still looking, this is our domain. And we said, okay, in this case, our x's are between two constants and our y's are between two constants, c and d. And then what we could do is imagine that maybe there was a surface above this. And so if we set up this double integral over, in this case, we'll call this r because it's a rectangle over r, of some function of two variables with respect to dA, right? dA was what, though? dA in our picture, just like dx was a little piece here and ds was a little arc length, the dA was what? Yeah, like this little infinitesimal little patch inside here, inside my rectangle, right? And so what we're doing is we're taking the height of the function times the little area of that little patch, and that gave us a little volume. Remember all those little boxes we added them all up, right? So that was something we could do. And then of course we had all sorts of different types of regions, right? We could do, like a type 1 region. We could do a type 2 region, right? And then after type 1 and 2, what did we do? Polar, right? And our polar regions look like that. So, but it's all the same concept. You have a two-dimensional domain, and then from there we define all this double integral, right? But all of them were with respect to area, okay? All right, anything else in 2D that we did? Wow, there was something else we did with 2D here, right? We did these line integrals, but then we moved on and did something else with these. We introduced vector fields, didn't we? Yeah. And we said if you're going to, let's say you're moving along this curve, but you're moving through some sort of vector field, then we could calculate this idea of like work or something like that. So back in here, we did all the line integrals with scalar functions, but then we introduced that work integral. So in here, we should probably throw that in here, that we did this thing, CF dot dr, right? That was in here. Okay. And then we actually did a closed curve too, right? Yeah. Started doing closed curves, and that gave us Green's theorem and a bunch of other things. Okay, what about three-dimensional? Three-dimensional. So that brought us our triple integral, right? So back with our domain. Oh, should we point out? We should probably point out with these, this one, we didn't. These we called D because they weren't rectangles. If we just did D1 dA, we said that was the volume, right? This is the I'm sorry, not volume, sorry. This is the area of D. For those of you who may came in a little late, I'm just trying to like recap some things here, because where we're about to go, I just want to make sure we got everything else kind of in some small order in our minds. Okay, so now in three-dimensional space, the first thing we did was we did a rectangular box in here, right? And then we did different types of these also. We could have like the shadow on the ground is like a type 1 or type 2 or even polar, and then we did cylindrical instead of polar, right? And then we did spherical coordinates. But all of these things we did in three-dimensional space, we basically set up triple integral over E, and then some function of three variables, and then dv, right? We did that. That would give us, well, we could find the mass of some solid object. We look at it as like the volume of a hypersolid, like this four-dimensional solid that you can't see. There's different meanings to this thing. And we also did this one, triple integral over E of 1 dv, which gave us the volume of E, right? What else have we done in three-dimensional space? Because it's not just triple integrals. We've done something else in three-dimensional space more recently. Pardon? Yes, that's coming. Okay, let's take that off the table for right now.
Then we do like also the line.
Yeah, we did curves in three-dimensional space, right? That curve, that path in two-dimensional space, we also extended to three. So we also had line integrals here in three-dimensional space. We had some curve, and then we could do line integral over C. But now it's a function of three variables instead of two. But it's still with respect to arc length, but this arc length is different than the other arc length because we're in 3D, we have three components underneath the square root and all that stuff, right? And then, you know, we could close this curve up, right? Or can we? Can we close this curve and use Green's theorem? Green's theorem was only two-dimensional, okay? So I wonder if there's a way we can close this up and have some sort of like Green's theorem. Does that make sense? Yes, we can. It's two sections away, all right? It's called Stokes' theorem. That's coming, all right? So we've done line integrals, we just haven't closed them up yet. This right here is still that little infinitesimal little arc length as you move along. I didn't talk about what these were. That dv was what here? In these solids? Yeah, a little cube in here, a little infinitesimal cube inside there is what this was, right? But ds here still has that same meaning, right? That same meaning, it's still arc length. Okay, so now I think that's good enough. What we're doing now is we've spent some time, last class, and take-home bonus, anyone else? I already collected it. Okay. We spent some time drawing surfaces in three-dimensional space, right? Surfaces. So what we have now is like we've got the solids, we've got triple integrals for that, we've got curves in three-dimensional space, we've got the line integral for that. But what if you have a surface in three-dimensional space? We're no longer wanting to look at the volume underneath it or any of that. Just take a surface and then imagine me saying, okay, here's a surface. Here's the density at every point. Let's find the mass of the surface. Does it make sense that we could do that? We just first need to be able to draw the surface. And that's what last class was about. So let's pick up from there. Let's start looking at deeper into this 13.6. And we're starting out with kind of, remember I was doing the notes here and then we broke away and did the examples? Okay, so now we're going to come back to the notes. It says here, the geometric meaning, oh wait, hold on a second. Did I go too far? Yeah, I went too far. Oops. So this idea of grid curves of a parametric surface. So we did several in class together, and every single one of them we were using U and V, right? And we were putting restrictions on U and V. And what I was trying to get you to see is that if you held one of your variables constant and let the other one go through its range, then it would draw like one piece of something, like one curve. Then you move the variable a little bit, it draws another curve. So like if we wanted to draw, let's say a cylinder like that, the outside of the cylinder, then we know we would need like cosine and sine to draw circles, and we just need to move the circles back and forth, right? Okay, so this idea of grid curves says if we hold U or V constant, it's supposed to say then our vector equation just draws space curves, just like we had in chapter 10, section 7. All right? Those curves are called grid curves. So I have an example here of a vector function that we have not looked at. We have not looked at this one in particular in this chapter, but we actually have seen this before. Do y'all recognize it? R of uv is sine u cosine v, sine u sine v cosine u. Do you recognize that? That looks like spherical coordinates, doesn't it? Except it's missing the row. So this is actually, this has a fixed row right now. What's our fixed row? 1, 1, 1, right? So you can go back and look at the section on spherical coordinates. We said we had like a change of variables. If you want to go from Cartesian to spherical, you had all these conversions, x, y, and z, yes? So if we do that, here's our definition of our vector function. This should draw a sphere. It should have a radius of 1, but it should just be the outside of it. That's all it should be, right? Just the surface. And u here is going to go between 0 and pi. That's our phi. Okay, and then our v is like our theta, which spins us around. All right? So I ask, do you recognize it? You do now, right? But let's see how this whole idea of grid curves works. So here's me having the computer draw grid curves. So I'm going to hold one of my variables constant. All right? So what I'm doing here is, looks like I'm holding my u, what was it u? Hold on. Which was the theta? The theta was v. Sorry, I'm holding my v constant here. Oh, it says it there. I didn't see that. Pardon? So I'm holding my theta or v constant here. And now what I'm going to do is I'm going to let my u move. And as I do that, that's like letting the phi go, right? And see, I draw that part of the shell of the sphere, yes? And then I can move my v a little bit, so I move it over. I draw another one. Now, it's not drawing it for me, but I'm going to just bring them all in here. So that's basically what you get here. Is as I move my u, I'm going to be on one of those, what do we call those lines that go like on the Earth? We call the lines these? Longitude and latitude, right? So if I hold one constant and the other one gets to move, I draw those. And if I hold that one constant and move the other one, I'm going to draw these. So you wind up getting, you get things like that, right? You get rings that go this way, or you get these half circles that go this way. Those are called grid curves, all right? Make sense? Kind of grids out your surface. Any questions? All right, so now, let's try and go back and remember what the derivative of a vector function of a single variable was. So when we were drawing curves in three-dimensional space using r of t, right? Remember, it was only r of t. It wasn't r of uv, just r of t. It would draw a curve. And then the derivative, r prime of t, would give us that red vector, wouldn't it? Remember this? Okay. So what about with these surfaces? What is the geometric meaning of the derivative of a vector function of two variables? Well, since you have two variables, it would only make sense to do the derivative if we hold one of the variables constant, like a partial derivative, right? So this is the notation we're going to use. The vector function r subscripted with u is the vector which is tangent to the space curve where v is held constant. So this is the partial, this is like the partial of r with respect to u, you're holding v constant. And then the other one, r subscript v, you're holding u constant, taking the derivative. But what is it going to give you geometrically? So here's our sphere, right? Here's our sphere. And what I'm going to do first is show you the partial of r with respect to u. So I'm going to be holding v constant. And what I get is this. So I'm holding v constant. So as I move u, remember, I'm going to draw around that piece. But do you see that green thing sticking out? That right there? That's the vector as you're that's the derivative, right? So that's like your tangent vector. Not really tangent because it's not unit length, right? But it's tangent, but it's not the unit tangent. And it's moving along, just along this curve. So it's just almost like you're back in chapter 10. Now if we do the partial with respect to v, this time hold u constant, we're going to go in the other direction. So now, let me move this guy around here. Now you've got those. Hey, I'm gonna kill one more light. I hope that's okay. Might help you see a little bit. So at this particular point, the partial of r with respect to u gives us that vector, which is tangent to the green curve. And then the partial of r with respect to v is going to give you a vector that's at this point on the red curve, but tangent to the red curve. Right? So do y'all see where we're about to go with this? Do y'all see what those two vectors are going to give us?
Yeah.
They're going to give us a tangent plane to that surface, isn't it? Can you imagine a tangent plane in here? I'm going to have a picture for you, but that's those two partials together give you two vectors that are tangent to the surface. And so how do we get a plane? What's the, you just need to cross those two vectors to get it, the normal vector, right? Okay, so that's geometrically what the partials are giving you, all right? So given a surface S with a vector function, r of uv, with u and v in some domain. So this is what that homework or take-home extra credit was all about. You came up with this function, you gave me the restrictions, right? So let's say we have that. We can now find the equation of the tangent plane at any point on the surface. So this is just finishing off what I just showed you. Move that guy. Oops. So there are tangent vectors, and then that will create that plane. And we should now be able to find the equation of that plane. All right, so let's do an example. There's no formal formula that I'm giving you here. You just need to understand the geometry of what's happening here. All right, so let's find the equation of the tangent plane to the unit sphere at that point. All right, so what we're going to need to do, let me write the point down. We're looking at the point root 2 over 2, 0, root 2 over 2. That's our point. Oops, almost wanted to do a vector there. And we are going to be working with the unit sphere, oops, which we just said is that vector function, right? right there. Okay, so you help me out. What do we need to do? Take the partials, okay? So remember, the equation of a plane looks like this. That's the equation of a plane, right? X naught, Y naught, Z naught is any point on the plane, which we already have. So all we really need to get is ABC, which are the normal, is the normal vector of the plane. We're going to get the normals by first taking the partials of this. So the partial of R with respect to U. So remember how to do that? You look at each component, you take the derivative, we're going to hold V constant. So what is the derivative of this with respect to U? Cosine U cosine V, right? Agreed? Okay, what's the derivative of this one with respect to U? Cosine U sine V. And then finally, negative sine U. So this right here is a formula that will give you the vector that is tangent to this surface, but only in one direction. It's only on the grid curve where U is changing and V is being held constant. Now we're going to need that at this point, right? Aren't we? But we'll get that in a second. How about partial of R with respect to V? So with respect to V, we should get negative sine U sine V. And then next one, sine U cosine V, right? And last one, just 0, right? Just 0. Y'all okay with that? Now, we're supposed to do what with these? If we want to get the normal vector, we're supposed to cross these now. So the normal vector that we are looking for should be equal to the cross product of these two. Now, we could right now, if we wanted to, we could go in there and try and figure out what U and V are. Because you have to be careful here. This is a point, right? This is not U and V. This is a point on the sphere. We have to figure out what U and V have to be to get us to this point. Does that make sense? Like this is not U, V, anything. This is an X, Y, and Z coordinate on the sphere. But we would have to figure out which U and V get us to that point. I'm not going to do that. I could right now figure out what U and V are, but I actually just want to torture myself and do the cross product of this. Just going to cross it right now. And then later on figure out what U and V are. So when we cross this, we cover this one up, right? And then we go here, here, like that, right? So what do we get on that first one? So this is going to be a vector. So 0 and then minus, but there's a minus already. So plus sine squared U, gosh, cosine V. Okay, next one, I cover this up. And I go here to here at 0. And then minus here to here, which would still be minus, right? But then I have to change it. So plus. Okay with that? Here to here. So plus what? Sine squared U sine V. And then finally, last one here. So we'll have a cosine squared V, and then we're going to have a sine U cosine U. So sine U cosine squared V. And then it's minus, but this one had a negative, so it should be plus. And what will this one be? Sine U cosine. So sine U cosine U sine squared V. There we go. Did y'all see anything we can do on that last one? take a sine u, cosine u out of both of those? If we do that, you'll have Pythagorean identity. So this is really all just going to turn into sine u, cosine u. Agreed? Okay. All right. Now, this is the normal vector at some arbitrary point on our sphere. We need now to nail down, where are we? How do we get to this point? So this is x naught, y naught, z naught, right? But it is not u and v. I already said that. So how can you figure out how you're going to get there? Yeah, we need this to be equal to that, this to be equal to that, and this to be equal to that, right? So which of those looks like the easiest to solve?
Cosine u equals root 2 over 2.
Yep, let's match up the last components. We know that cosine of u must be root 2 over 2. But remember, u has to be between 0 and pi, so what does u have to be then? What angle do I take cosine of to get root 2 over 2?
Pi over 4.
Pi over 4, right? Cosine of pi over 4 is root 2 over 2. So u must be pi over 4. All right, let's go after another equation here. How about that middle one? We know that sine of u, sine of v must be equal to what? 0, right? 0. Now, we know what u is, right? U is pi over 4. So what is sine of pi over 4?
That's also root 2.
That's also root 2 over 2. So root 2 over 2 sine of v must be 0. I can divide both sides by root 2 over 2. I still have sine of v is 0. And now, when does that happen?
Pi 0, 0.
When, what?
Or 2 pi.
Yeah, we actually have 2 points here. V is equal to 0 or 2 pi, right?
Or pi, right?
Wait, hold on. We are restricted between 0 and 2 pi. Yeah, we have 3. Why did I put 2? I don't know why I said 2. It's all of them, right?
Oh, right.
It's all of them, right? Now, let's look at the last condition. All right, let's look at this last condition. Make sure we have all conditions satisfied. We know the last components match, right? Cosine of u is this. We know that sine of u, sine of v is 0. But what about that first one? We need sine of u, cosine of v to be equal to what? Root 2 over 2. We already knew what u was, right? So that's pi over 4. So sine of pi over 4 is root 2 over 2. So we have root 2 over 2. Cosine of v must be root 2 over 2. Divide both sides by root 2 over 2, and you get cosine of v must equal 1. So now what can you tell me about v?
It's only 0 or 2 pi.
Yeah, it's only 0 or 2 pi, right? We can throw out the pi, because cosine of pi is negative 1. So pi will satisfy the second part, but it won't satisfy the first point. Now 0 and 2 pi are going to wind up being the same point because you're drawing the sphere, right? So when you get all the way around, you're back where you started. So we're talking about a unique point on the sphere. All right, let's get our normal vector. Any questions on that part? You have to recover what u and v are, and now you can go get your normal vector. So would y'all mind doing that real quick? You know what you need to do?
Plug that in.
Yeah, I would use for u, I'd use pi over 4. And for v, to make it easy, I'll just use 0. So take that in here, right? Plug it in for this. That'll give you your A, B, C. Just give me just a second, I'll be back. What's the equation of this sphere? I'm going to put it down here. Don't yell it out, please. Okay, raise your hand. Don't disrespect one another. No? Don't have it yet? No?
So the root 2 over 2 and 0 and the root 2 over 2, that was given to us, right?
Yes, that was given.
So for the normal vector.
For normal vector?
you can see I got just 1/2, 1/2, 1/2.
1/2, 1/2, 1/2. Anyone else get that? All right, I'll go with it. So you're saying it's 1/2 and then x minus what?
It's
Root 2 over 2 and then plus 1/2 and then y minus 0, so just y. And then plus 1/2 z minus root 2 over 2 equals 0.
For the second term in the middle, I got 0.
You got 0 in the middle?
Because the sign of z is
Okay.
going to be 0.
Yeah. Change back to 0. Okay, so this is 0. Okay. Are y'all okay with that? All right, I'm gonna check your work now. So what I'm gonna do, I was hoping y'all would just work that out and I'd come back and check it. So let's see. How am I going to check it? I'm gonna go and see if I can graph it. I'm gonna try and see if I can get the computer to graph the sphere, the point, and your plane. And they should all come together. So let's see if it does. Desmos. Have I used Desmos? I have a little bit, right? Okay, so Desmos is pretty cool. I'll show you something about this graph. How many of you have used this? Anyone use this? Yeah? Do y'all know about this feature? Like if you do x squared, like cool, you draw a parabola. But if you put like something in front of it, like a times x squared, then you can add this thing called a slider, and then you have the control over a. So you can change, and then if you wanted to, you could do something like plus b times x, add a second slider, and then you could even say like plus c and add a third slider. And now you have the ability to completely control a general quadratic function. Pretty neat, huh? Okay, but we're not doing that. That's not why we're doing this. I show you that because I can remember years ago when that functionality first came to Mathematica, which is the program I use, and that was a huge, huge deal to be able to control something like that dynamically. But now you can just go to a website and it's there. Okay, so let's start with the equation of the sphere. Let's see how Desmos does with this. I'm actually not sure.
I think it does 3 dimensions.
Does it not do 3?
It does not do 3.
Ah, Desmos, you're letting me down here.
I think they're working on it.
They're working on it. Okay, so I may not be able to show you. That's terrible. Okay, so the best I think I'm going to be able to do is to show you the plane, show the partials. Let's go out here. It was pi over 4 and then 0, right? Let's just look at my code real quick because that'll maybe tell us. Nah. You know what? I'll look to see if I can find some other graphing software because, I mean, you can kind of tell here that it's working because we've got pi over 4. Was it u is pi over 4? Pi over 4 and then v is 0. And if I plug that in, I'm at this point. It's drawing me this. All we'd have to do here is verify that the derivative is correct. So let me come up here. Where was our derivative? This might be too much. Yeah, let's not get into this. I don't want to go find it. Yeah. Sorry. You trust your answer?
Yes.
All right, good. Okay, so now, what can we do with this? So let's go back and remember I started class with this idea of, we had a curve in 2-dimensional space. And if we do this integral right here, that would be the length of that curve, right? The idea here was that what you're going to do is you're going to move along here and take a little tiny little arc length, right, your ds, and then you're going to multiply it times 1, which means it's still ds, and then you're going to just add them all up. So you add up all the little arc lengths and you get your length of your curve. Well, what if we want to know the area of a surface now? Right? The area of a surface. So what we're going to do is this. We are going to do a double integral, okay? So we have some surface, got restrictions on u and v. We're going to do a double integral over d of the cross product. So what is this piece right here? What is that? Normal, the normal plane, right? But magnitude. What's the magnitude of the cross product? Ooh, this is going way back. If you take two vectors, let me show you two vectors, right? If you take two vectors and you take their cross product and you take the magnitude of it, what does it give you? No. So this is back in chapter 10, so it's been a while. The cross product of two vectors, you take the magnitude, it gives you the area of the parallelogram that they form. So this vector and this vector form this parallelogram, don't they? The magnitude of the cross product gives you the area of that parallelogram. So what we're doing here is we're saying, hey, look, we're trying to find the surface area of this sphere, all right? So imagine we want to try and find the surface area of that little patch, just that little patch right here. Then what we do is let me get down to the patch. The surface area of that little patch is not the cross product of the magnitude. I'm sorry, it's not the magnitude of the cross product of the vectors, right? The partials, because that's the area of this green thing, right? We actually want to scale that. So we want to somehow scale this vector back and scale this vector back to give us that little patch. So what we do is we scale it by a little differential. And the little differential that we scale it by, which we did this back when we did this, we did the same thing. You just have to go back and look in your notes. We're not going to get too in-depth and back into it, but we did this already. This ds, when we did this, this turns into a square root of something, dt. And that dt was the thing that helped scale things back. So we're scaling things back, and that's what the dA is going to do. dA is going to scale this thing back so that it actually becomes the patch, if that makes sense. Okay? Just geometrically, that's what's happening. So let's see if we can't use that to verify the formula that we have in our books for the surface area of the unit sphere. So if you go into a textbook and they draw you a sphere of radius r, they will tell you that the surface area of this is what? 4 pi r squared. Okay, that's what's in your formula sheets, right? Okay, so we want to verify that this is true for a unit circle. So what should our answer be for this problem? Okay, but it's a unit sphere, so just 4 pi. Okay, so let's just verify that the surface area of a sphere is 4 pi. So what do we need to do? We need to do the double integral over d of the magnitude of the cross product of the partial derivatives, dA. Okay, so remember our restrictions here. Our u was between what and what? And our v was between what and what? I'm getting them mixed up. U is 0 to pi here and 0 to 2 pi here, right? Those are our restrictions. We already did the cross product a second ago, didn't we? But we need to take the magnitude of it. All right, so we've already done part of this computation. So if someone doesn't mind reading out to me what this was, since I erased it, this vector. What was it? Yeah, that was from the normal, because to get the normal vector, we did that cross product, didn't we?
So it was sine squared u.
Sine squared u cosine v, and then
Sine squared u sine v.
sine squared u sine v,
Sine u cosine u.
sine u cosine u. Okay, so that was the normal vector, which is really just these two crossed. Now we need the magnitude of that, right? So let me find the magnitude of this. The magnitude of this should be the square root of the sum of each component squared. So I need to square this, sine to the fourth u cosine squared v, plus sine to the fourth u sine squared v, and then plus sine squared u sine cosine squared u. All right, can we do anything there?
Well, like sine squared, cosine squared, first two terms.
Yeah, so here on these two, you can pull out what? Sine to the fourth u, right? And what would you be left with? Cosine squared v plus sine squared v, which is 1. So we really just have here sine to the fourth u, and then this is still here, plus sine squared u cosine squared u. Now what can I do here?
You can split up the sines to the fourth to sine squared, sine squared.
You could do sine squared right there. What do both of these have in common though?
Sine squared.
Sine squared u, right? So why don't you pull a sine squared u out of that? Right? And then you'd be left with what? Sine squared u plus cosine squared u, which is 1, right? So this is going to give you the square root, because that's a 1. This is the square root of sine squared u, which is just sine u. I mean, technically it's the absolute value of sine of u. But I'm going to say it's just sine u. Why do I know that that's positive? Why do I know that that's positive? Why do I not have to do absolute value here?
Sine is always positive from 0 to pi.
Yeah, between 0 and pi, right? Sine is always positive, so that's okay for me to do that. Milton, what are you drinking today? You got something different today, don't you? Just messing with I'm just messing with you, Milton.
Sure.
All right, so we got that? Okay, questions? We need to integrate that with respect to area. So let's come back over here. I need to do the double integral. And now I'm going to go over D, which were my restrictions. These are both constants, so the order in which I do this does not matter. So I'll go, let me go 0 to 2 pi, so I'll do V on the outside, 0 to pi here. I'm integrating sine u du dv. Make sense?
Sure.
Okay, this should give us 4 pi. Let's see. What is the inner integral? Antiderivative of sine of u is negative cosine of u, and I want to evaluate that from 0 to pi, like that. And then after I'm done with this inner integral, I still have to integrate that with respect to v. So 0 to 2 pi. Okay, let's plug in pi first. So cosine of pi.
-1.
-1, but then minus. So plus 1, so I have 1 here, minus, and then 0, cosine of 0 is 1, so -1, so -1 here, like that, dv, right? And that's going to give us 2. So integral from 0 to 2 pi of 2 dv, the antiderivative of that is just 2v, and we're going to integrate that, or evaluate that at pi, and what am I missing here? 2 pi up here, sorry. So plug this in here, what do you get? 4 pi minus 0. So we just verified, okay? We just verified it. Now, let me ask you something. Let me ask you something. Do you all follow that?
Yep.
Okay. Let me go back to this something right there. When we define this, right? Too big. What if I had given this, but I had put in here row, row, row? Okay, that would have been a constant, right? But I wouldn't have, it's not a variable, it's just I'm just fixing it at row, right? So that means there's a radius of row for this one, right? Okay, when I did my partial derivatives, what would have changed? When I did my r subscript u and my r subscript v, what would have changed? Nothing, but I would have rows the whole way, wouldn't I? Would have had rows in front of everything because the constant would have come for the ride. And then when we did cross products, right? When we did cross products, what would have happened? You get some row, what do you think, row squareds in there,
Probably.
right?
But then when the square root just cancel out.
So imagine that you had right here, like row squared here, row squared here, row squared here, right? Agreed? And then when you were in here, all of those would come in, right? What would they become? Because remember, these are the cross products. You have the row squareds here. But when you do this, you would get row to the fourth here, row to the fourth on that one, row to the fourth on that one. And then when you pull the row to the fourth out of everything, right, and then took the square root, it would go back to row squared. So the only thing that would change here is you would have had a row squared here, right? And then at the end of this whole thing, the row squared would have just come along for the ride, and just at the very end, you would have had your row squared there. So if what I'm saying is that if we just would have done this problem with row in the very beginning, right, not a unit sphere, but a sphere of radius rho, then we would have come out with the formula that's in the back of the book, which is 4 pi r squared. All right. So we know we can find the surface area. Now, what about a very special case? Okay, is a sphere a function of two variables? Like our traditional function of two variables. Can a sphere be drawn using z equals f of x, y? Can we draw a sphere using that right there? No, because it fails kind of like the vertical line test from college algebra. Like we could draw this if we did the top half and the bottom half separately. But if you give me an x and y, like in the domain, if you give me some x and y coordinate, then the z has to go to the top and the bottom. So it's not a true function because you'd have to have two outputs. So we know that for a sphere, we can find the surface area, right? But it's not a true function of two variables like this in this sense. So this is a special case. It says, what if the surface you're actually trying to work with is a function of two variables? What if it is? Then what you can do is you can go and look at your component functions. You know how we've been using u and v? You just say, okay, let the first component function, let that just be u, the second one be v, and then let the last one be this function of u and v. So it's kind of like your inputs are x and y, and then your output is z, all right? Then what happens is, and we're not going to go through all the arithmetic of this, but if you do the partial derivatives, well, maybe we will. It's not that hard to do. What we're saying is that our r of uv will now be u, v, and then this one, what do we, g? I use f, so f of uv. So it's like the x, y, and then here's your z as a function of those two variables. What would the partial of this with respect to u be?
With respect to the u,
Yep,
just one.
1. 0, and then whatever the partial of that is with respect to u, right? And then what would the partial of r with respect to v be? 0, and then 1, and then the partial of whatever that is with respect to v. And when you do this cross product now, right, when you do the cross product, what would we get? Partial of r with respect to u cross with partial of r with respect to v. We get a nice vector here, right? Cover this up, we get 0 and then minus that. So minus partial of f with respect to u. And then do the middle one, this one, and 0, right? But then change the sign. And then what about this last one? 1. Okay, that's the cross product. And now you need the magnitude. So if I take the magnitude, square root of that squared plus that squared plus that squared, right? Which is that. Okay, do y'all see that? Sure? So in the special case, in the very special case that the surface is some function of two variables like we've seen in the past when we were doing like double integrals and things like that. When we have that special case, then the formula for surface area just becomes this thing with respect to A. All right? So we don't have to actually go through and calculate the cross product in magnitude. We can just go straight to this. And we're going to do that in an example right now. All right. Find the surface area of the paraboloid z equals y squared minus x squared, which lies between the cylinders x squared plus y squared is 1 and x squared plus y squared is 9. Okay, this is a weird surface to even like kind of put your head around, like what it looks like. So do y'all know what this looks like? Z equals y squared minus x squared. It's a surface, right? Some sort of surface. What does it look like? What does it look like when x is 0? What does that thing look like?
Y squared.
Y squared. So if this is x and this is y, when x is 0, this thing looks like this, right? Looks like a parabola. And then what does it look like when y is 0? So when y is 0, it looks like this. So this is one of those weird shapes where you have, like, in one direction it's like this, right? Like this. But this side gets pulled down and the other side gets pulled down. So it's like a saddle. Do y'all kind of visualize that? A little bit?
Yeah.
Okay. So you got this like saddle shape. And you want the surface area of that saddle, but only between these two cylinders. So these cylinders open which way? Like up, right? Like through the z-axis is like the center. This one has a radius of 1. This one has a radius of 3. So you're trying to find the area of the surface, this surface, but only between these two. So I'm not sure. Is this what you were visualizing? Okay, so again, if we bring everything in, we have the weird saddle shape, and then we have the two cylinders, and we're trying to find the surface area of this thing between these two. So take that out like that. Does that seem like a very challenging question, though, just in general? Like, look at that shape, what's its surface area? Well, it's not going to be that bad.